Hello, everyone. Good to see you. Welcome. Happy Monday. Hope you had a nice weekend and are enjoying our Santa Barbara winter here. Those of you that are in Santa Barbara, it's just unbelievable. It's beautiful, beautiful, beautiful. I hope you all got my email for this week. I know I had some big, scary red writing at the top about what's coming up. And I just wanted to warn you that the next 3 to 4 weeks are probably the toughest of the year in terms of the material. I don't want to scare you. I just want to encourage you. It's not that it's undoable. It's totally doable. And you guys have stuck with it this far and have done well. And so you can master this material. But I just want you to know it's a little more challenging. Okay, it's definitely the most challenging material of the year. So with that, all that means, and we have about 3 to 4 weeks of it, and then it gets a little bit easier again. Okay, so if you can stick with me in these next 3 or 4 weeks, and just do a couple of things, not fall behind. Very important with this material, not to fall behind. Why? Because it's very cumulative. Everything we do from here until about 3 to 4 weeks from now is going to build on itself, right? So if you fall behind, it's really hard to understand the next step. And if you fall behind again, it's hard to understand the next step and so on. So super, super important that you stay right on top of it. Every day that we have assignments due, stay on top of those assignments, stay on top of the problem sets, stay on top of the lectures. Don't let yourself fall behind. And then just budget a little bit extra time for this material, because it'll take a little bit more time probably for this class in the next 3 or 4 weeks than it has the rest of the year. Okay. And then I promise it'll get easier again. Fair enough? But if you stick with it, you'll learn some cool things, and hopefully you'll have a little fun with it as well. Okay. Because it's all important stuff. It's things like equilibrium, which we're doing right now. And then we're going to get into acids and bases, which are also very common and very interesting. And then we're going to get into things like buffers and titrations. And so it's a lot of interesting topics, but they're just a little bit challenging, and they just build, they're very cumulative, right? That's the main difference. Okay. I'm going to go ahead and get started on equilibrium concentrations. But before I do, let me pause for a second and see if there are any questions. All right, I don't see any questions, so I'm going to go ahead and get started. So you know we've been talking about equilibrium this chapter, right? And just before this, we were looking at calculating equilibrium constants, right? So if you know the equilibrium concentrations, right? If you have any chemical reaction, right? This is just a generic one, right? You can express the equilibrium constant with regard to concentration as the concentration of the the concentration of the products, each raised to their stoichiometric coefficients, divided by the concentration of the reactants, each raised to their stoichiometric coefficients, right? And we saw that if we could figure out the equilibrium concentrations of all these things, right, we could get Kc, right? We can calculate Kc, all right? And we've been doing that. We also learned about the reaction quotient, which essentially has the same form as this, but it's defined anywhere in the reaction progress, right? And it's a measure of where you are relative to equilibrium, right? So remember what we said last time. Suppose the equilibrium constant was 10 and the reaction quotient was 1. What would that tell you about where you are relative to equilibrium? Is the reaction going to go to the right towards products or to the left towards reactants?
Can you repeat that again? Sorry. Wait.
If the let's suppose that the equilibrium constant is 10. So let's say Kc is 10 and Q is 1. Which way is that reaction going, right or left?
Right.
Yeah.
Right.
Right is correct. All right. It's going to the right because Q is less than K, right? If Q is less than K, the reaction is going to the right. It's going to form more products because Q eventually ends up at K, right? And if Q was 100, right, and K was 10, it would be going to the
Left.
Okay. All right. So that's the reaction quotient and calculating equilibrium concentrations. Now, what we want to do is we want to be able to find equilibrium concentrations. And there's two types of problems where you got to find equilibrium concentrations, all right? The first one is easy, relatively easy. You're given the equilibrium concentrations of everything but one product and have to find it. So for example, you'd be given K and you'd be given the concentration of A, B, and C. Then you have to find the concentration of D, right? Pretty straightforward. You just solve this equation for the concentration of D and figure out what it is, right? And then the second class of problems is a little bit more difficult. And that's where you're only given the initial concentrations and then have to find the equilibrium concentration. So for example, in this reaction, you might be given the concentrations, the initial concentrations of A and B, and then say, okay, when it gets to equilibrium, what are the equilibrium concentrations? Okay. This second problem is going to be the more common one. And we're going to do a lot of this second type of problem in the next 2 or 3 weeks. All right. So it'll be important to understand this second kind of problem. But let's do the easy one first because it's fairly straightforward. And let's go ahead and bang this one out. Suppose you have a sample of PCl5 and it's placed in a 0.5 liter container. All right, so you have volume is equal to 0.500 liters. And you have this reaction, PCl5 in equilibrium with PCl3 plus Cl2. Okay, and those are all gas. So we'll put in all the gases. And then it says at equilibrium, you have 0.203 moles of PCl3 and 0.203 moles of Cl2, right? And you want to find the equilibrium concentration, find the concentration of PCl5, right? And they give you the value of K. Kc is equal to 0.0635, right? So what you have then is you have the equilibrium concentrations of 2 of these guys, and you got to find the equilibrium concentration of the third. Now notice that you're given moles and volume. You're not given molarity. What gets plugged every time into the equilibrium expression? What gets plugged into here? Moles or molarity?
Polarity.
Molarity. Okay. If it's Kc, it's molarity. If it's Kp, it's partial pressure in atmospheres. Okay. So either whenever you plug in a K, it's either going to be molarity or atmospheres. Okay. Nothing else. Never just moles. You have to have molarity. Okay. So let's just figure out the molarity of those two things. We could just plug it in. Well, let's just do it like this. Kc is equal to the concentration of PCl3, concentration of Cl2, divided by the concentration of PCl5, right? So then we can solve that for the constant. We're trying to find the concentration of this thing, right? So the concentration of PCl5 is equal to the concentration of PCl3 times the concentration of Cl2 divided by Kc, right? And so we don't know the concentrations, but we know the moles and the volume. So we can either calculate them out and plug it in or just plug those in directly. So let's just do that. PCl3 is going to be 0.203 moles divided by 0.500 liters, right? Concentration of Cl2 is going to be the same thing, 0.203 moles divided by 0.500 liters, okay? And then we're going to divide by Kc, which is 0.0635, right? Notice again, what I'm plugging in here is not moles, but concentration, right? Moles divided by liters, all right? And so if I just crank that out, I get 2.60 molar. All right, fairly straightforward kind of problem, right? You have a reaction, you know the equilibrium constant, you know everything but one thing, you just solve for that one thing. Okay. Let's have you try it. Go ahead and try this one. Okay, about 15 more seconds. 15 more seconds, see if we can finish it up. All right, I'm gonna go ahead and end it right there. Nice work. The right answer was B, and most of you got that. A few of you didn't quite get it, but most of you did, so nice work. Let's see really quick how you do that. So you got the expression for Kp, right? And look, you're given the concentration of N2O4, so you're given this, right? And you got to solve for NO, right? So the concentration of NO squared is equal to Kp times the concentration of N2O4, right? So the concentration of NO is equal to the square root of Kp times the concentration of N2O4, right? So you just plug those things in. Kp is 0.133. And the concentration of N2O4 is, what is it? 2.71 ATMs, right? And that gives you, sorry, it's not concentration that we're solving for, it's pressure, right? Because this is Kp, my bad. PNO, 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 and that gives you 0.600 atmospheres. All right, so there it is right there. Does that make sense? Awesome. Okay, very good. Now, let's move on to the second class and the more difficult kind of problem, and the kind of problem that we'll be working a lot in the next few weeks, okay? And that's kind of problem where you are given initial concentrations and have to find the equilibrium concentrations. Okay, you're given the initial concentrations and have to find the equilibrium concentrations. So here is an example. You have A gas in equilibrium with 2B gas, right? And you're given Kc is equal to 0.33. All right, and you're given the initial concentrations. Initial concentration of A is 1.0 molar. Initial concentration of B is 0.0 molar, right? And it's asking you to find the equilibrium concentrations. Right, find the equilibrium concentrations, okay? So this kind of problem, what you have to do is you have to recognize it as this kind of problem, all right? And by the way, that's going to be one of the keys to the next 3 or 4 weeks. Recognizing what kind of problem you have. Because a lot of them are going to look kind of similar, right? Like this looks a little similar to the problem we just did, right? But let's see, was there a question? What was after P sub? P of NO is equal to square root of 0.133 times 2.71 atmosphere. So yeah, I messed up. All these concentrations that I put in here should really be partial pressures. Right? I accidentally put concentrations instead of partial pressures. My bad. All right. All right. So in this kind of problem, yeah, we're finding these equilibrium concentrations. So you got to recognize it. And the first thing you do every time you see a problem like this is you make an ice table. Okay. That's the first thing you do is you make an ice table every single time. So use the reaction as the guide for the ice table, right? So write the reaction, right? Across the top, and then write initial, change, and equilibrium along the left side, right? And then go ahead and plug in everything that you know, right? So the initial concentration of A is 1.0. The initial concentration B is 0, right? And that's all you know so far, right? And you're given the equilibrium constant, All right, now here's the key. The next step is you have to figure out which direction the reaction's going, and you got to set that up in terms of a variable x that you're then going to solve for. Okay? Figure out which direction the reaction's going and set it up in terms of a variable x, which then you're going to solve for. So if this is 1 and this is 0, which way is this reaction going? To the right or to the left?
The right.
To the right, right? Because Q is essentially 0. Q is 0, right? So it's going to the right. So we're going to say, okay, if it goes to the right, we're going to set this up as minus x. That's the basically the amount that it's going to the right in terms of the amount of A, right? The concentration of A. And if this goes down by minus x, then this goes what? Up by
Positive X.
UX.
positive
2.
2x, right? The 2 is hugely important, right? Why is it plus 2x? Because look, there's a 2 here, right? So we know from stoichiometry that if 1 mole of this reacts, it forms 2 moles of that, right? So if x moles of this reacts, I get 2x moles of that. Okay? And then, as is common in ice tables, you're going to sum 1.0 minus x and 2x. Those are my equilibrium concentrations in terms of the variable x. Yeah? And then you're going to plug into the equilibrium expression. So write that out next. Kc is equal to the concentration of B squared over the concentration of A, right? And then you're going to go ahead and take the concentrations from this equilibrium line and plug them into here. So I'm going to plug this into there, and I'm going to plug this into there, right? So I'm going to get Kc is equal to 2x. Now be very careful here. This is a very common mistake. 2x, the whole thing squared, okay? It's 2x, the quantity squared. It's not 2x squared. So this is going to end up being 4x squared when I square everything. And then divided by the concentration of A, which is 1.0 minus x, okay? So I end up with something like 4x squared over 1.0 minus x is equal to 0.33. Then I got to solve that equation for x, okay? Now, a lot of the time, you're going to get an equation like this, which is a quadratic equation, all right? So you're going to have to reach back to the days you took algebra and remember how to solve quadratic equations, all right? You got to use the quadratic formula and solve it. It's 4x squared, right? Because it's, remember when you have AB squared, that's equal to A squared, B squared, right? So 2x, the quantity squared, is 4x squared. So you solve the quadratic equation, you solve it for x, and then what do you do to get the concentrations? You're going to know that the concentration of B is just going to be equal to 2x from this line, and you know the concentration of A is just going to be equal to, from this line, and then you know that the concentration of A is just going to be able to 1 minus x from that line, okay? The key is you got to solve this equation for x, and that requires a quadratic. There are some shortcuts, and I'll be showing you some shortcuts so you don't have to always solve a quadratic, all right? Now, I'm going to say this about solving quadratic equations. You should be able to do this, right? You've had algebra, you know how to solve quadratic equations. They're also very time-consuming to solve. So I would first look for shortcuts to solving them, and I'll show you some of the shortcuts here in a minute, all right? Secondly, if you have to solve a quadratic, you know, do one by hand so you know how to do it just in case, but you don't have to do it over and over again, all right? If you have a calculator that solves quadratics, you can use that. There's a lot of programs on the internet that'll solve quadratics for you, all right? If you don't know of any, there's a site called Wolfram Alpha. You can go to that website, you can plug in your quadratic and it'll solve it for you, okay? And I don't mind you doing that. And for the exam, you will be allowed to use a calculator that solves quadratics or a website that solves quadratics if you need to, okay? All right, so that's the idea. Let's look at a couple of real problems, all right? So these are a couple of examples from the book. You can just follow along because these are in the book. You can go back and review them from the book. But First, notice the kind of the way the problem is stated. A reaction mixture initially contains nitrogen at 0.2 molar and oxygen at 0.2 molar. So you have the two reactants. Find the equilibrium concentrations, right? The minute you hear that, ding, 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 it should be like programmed in your head, right? Initial concentrations given, equilibrium concentrations find. Okay, I know I got to draw up an ice table, right? So you draw up your ice table, you use the balance equation as a guide, right? It's giving you the initial concentrations of 0.2, 0.2, and 0, right? Then you got to decide, okay, so let me just write this ice table here. You got N2 plus O2 in equilibrium with 2NO, right? And initial change equilibrium, right? You put in the initial concentrations. So good, so far so good. Which way is this reaction going? To the right or to the left?
To the right.
To the right. Anytime you see a 0, right? It's always going to go in the direction of the 0. Okay, because it's always going to fill that in, right? Notice in this problem, it says a reaction, you have this reaction and you have NO2 at 0.1. So here you have some products and then you have a reactant. Which way is this reaction going to go?
Left.
To the left, right? This one's going to the left, this one's going to the right. But let's focus on this one for right now, okay? So again, we're going to set this up in terms of the change in terms of the variable x, right? So we're going to say N2 is minus x, O2 is minus x, and then what's NO going to be?
2x. Or no. Wait.
2x.
Would it be 2x?
Plus what?
2x?
2x, correct. Plus 2x, right? So this is going to be 0.200 minus x. This is going to be 0.200 minus x. And that's going to be 2x. Does that make sense? Okay, so then I'm going to write out the equilibrium expression. Kc is equal to the concentration of NO squared divided by the concentration of N2 divided by the concentration of O2. Right? And then I'm going to plug in. This is going to go there. This guy is going to go there. That's going to go there. Right? Notice I'm plugging in from my equilibrium line in the ice table. Okay? So I'm going to get I'm going to get that. Kc is equal to 2x, the quantity squared, over 0.2 minus x, 0.200 minus x. So Kc is equal to 2x, the quantity squared, over 0.200 minus x, the quantity squared. You with me? So now this is one of those shortcuts. Now there's a couple ways to solve this. You can multiply this out, right? And you'd end up with a quadratic equation and you can use a quadratic formula, right? Or you can realize that, oh my goodness, since this is squared and this is squared, I can just take the square root of both sides, right? That simplifies it quite a bit, right? So if I plug in, and now I'll just go to here real quick and I'll show you. So this is what we just did, right? Minus x plus 2x. Again, that 2 is there because there's a 2 there, right? So there are your equilibrium concentrations. You plug into here, you get 0.1 is equal to 2x the quantity squared over 0.2 minus x the quantity squared. You take the square root of both sides, right? So when you do that, and you solve for x, you get that x is equal to 0.027. But notice it's fairly simple to solve for x. You don't have to solve a complicated quadratic or anything like that. Okay. Once you get that, then you got to go back to this equation to get the concentrations, right? Or to this line, right? So the concentration of N2 is going to be equal to what? 0.200 minus x, right? Concentration of O2 is going to be equal to 0.200 minus 0.027. And the concentration of NO is going to be equal to what? 2 times 0.027.
Do you
Right?
mind looking that paper up, please?
Sorry. Again, those come from this last line. And plugging x into there, right? So if I multiply those out, I get what? 0.173 molar for this. I get 0.173 molar for that. And I get 0.054 molar for that. So there are my equilibrium concentrations that I'm trying to find.
Quick question.
Yeah.
Did you find x after finding the square root of 2x over 0.200?
Correct. So this equation is basically, remember this was 0.10, right?
Mhm.
So 0.10, I take the square root of that. And when I get the square root of that right here, I follow along right here, I'm moving over to here, right? I take the square root of both sides. So I get the square root of 0.10. And then when I take the square root of that, I just get 2x over 0.2 minus x,
Yeah.
right?
Okay.
So then I just, bring this over there. I get square root of 0.10 times 0.2 minus x is equal to 2x, right? All I did is I brought that over to the other side.
Mm-hmm.
Then I multiply that together, right? Multiply that through. So I get square root of 0.10 times 0.2, square root of 0.10 times x. As I multiply that through, that's equal to 2x. So 0.063 is equal to, so that's just that multiplied together is equal to 2x plus that. And I just solve that for x.
Okay. Yeah.
Does that make sense?
Yeah.
Okay. So shortcut number one to look out for. Look out for this in your problem set. Look out for this in exams, right? Because it saves you a lot of time. When you see a perfect square, right? Notice here I have 2x squared over 0.2 minus x squared, right? That's a huge time saver, right? Notice the difference between that and the equation we did here, right? No perfect square here. In that case, I have to multiply it out and solve a quadratic equation, all right? Or again, like I said, plug it into Wolfram Alpha or, and by the way, if you want to know how to use Wolfram Alpha, stick around after class and I'll show you, okay? Stick around after class and I'll show you how to use Wolfram Alpha, okay? Anyway, that's a big time saver. Okay, let's look at this other problem on this side, okay? So in this case, we said it's a different equation. The reaction is going to go to the left, all right? Because Q is basically equal to infinity, right? The reaction goes left. So in this case, I'm going to put in my x's. This is going to be minus 2x. Again, it's minus 2x because of the 2. Sure, I can record it. Minus 2x. And this is plus x, right? Because it's going to the left, all right? Then I sum this up at equilibrium. I have x and 0.1 minus 2x. I just sum those up, right? Now when I plug in a Kc, the concentration of NO2 is 0.1 minus 2x. So I'm going to put 0.1 minus 2x, the quantity squared. Concentration of N2O4, I'm going to look here. That's just x. So I get x on the bottom. And now I have this lovely quadratic equation, right? Lots of fun. So here's how you solve it by hand. You got to get it into the quadratic form, right? So you take this, multiply both sides by x, and you get this, right? And then make it, subtract that from both sides, and you get this equation 4x squared minus 0.76x is equal to 0.1, right? That's the quadratic form, right? Do you guys remember this from algebra? Ax squared plus bx plus c equals 0, right? You got to get it into that form. That's the quadratic form. And then from there, you can use the quadratic formula, right? The quadratic formula is x is equal to minus b. Remember, this is b in this case, plus or minus the square root of b squared minus 4ac, all that over 2a. All right. So then you take a, b, and c and you plug it into there, and you're going to get a quadratic equation usually has two roots, all right? Two answers for x, both of which work in the math. So that's why you have this plus or minus, right? So you get 0.76 plus 0.65 over 8, and you get 0.76 minus 0.65 over 8, right? These examples are on page 704 in the book. Okay, now remember, if you go back, the concentration of NO2 is 0.1 minus 2x. What will happen with these two roots is that one of them will usually give a negative number. And you can't have any negative concentrations, right? So you reject the root that gives you any negative concentrations, and you stick with the one that only gives you positive concentrations, right? So you plug that into into x here and here, and you find the concentrations of NO2 and N2O4. All right? Does that make sense? You can always check your answer. The way you check your answer is you just take your concentrations, plug them back in, and you should get the equilibrium constant back, right? And in this case, it was given as 0.1 and you get 0.097. That's close enough. And similarly here, you get 0.37 by plugging those concentrations back in, and close enough, okay? All right, so approximations to simplify the math. So remember, perfect square, right? If you see the perfect square, you think, that just saved me 10 minutes of time, right? Another very important approximation that we're going to be using a lot is what I call the x is small approximation. And here's the analogy. Let's say you go and weigh yourself. Okay, you weigh yourself and you weigh 160 pounds. Then you weigh yourself with a penny in your pocket. So you get on the scale again with a penny in your pocket. Actually, let me do it the other way around. First, you weigh yourself with the penny in your pocket. You weigh 160 pounds. Then you take the penny out of your pocket and you weigh yourself again. Is there going to be any difference in your weight? No. On the accuracy of the scale, you're not going to notice the penny. Okay? That is the concept of the x is small approximation. When you subtract a small number from a big number, the small number is insignificant, right? If I have a number like 99, let's say, and I subtract, let's say I have 99.0 minus 0.0005. What's that equal to the correct number of significant figures?
99.0.
99.0, right? It's still equal to 9. This is the penny, this is you, right? Subtracting the penny out from your weight doesn't change your weight, right? Because it's insignificant compared to the weight. That's the idea of the x is small approximation, right? Notice though that if I multiply a big number by a small number, you have to do the multiplication. You can't ignore the small number in multiplication, right? You can only ignore the small number if it's addition or subtraction, right? Okay, so that's the x is small approximation. So let me give you an example. Here's the same problem we did earlier. A in equilibrium with 2B. You're given Kc, but now Kc is going to be a lot smaller. 3.3 times 10 to the minus 5 instead of, what did we have earlier, 0.33 or something? So this is a lot smaller equilibrium constant. Again, they're giving me the initial concentration of A is equal to 1 molar. Initial concentration of B is equal to 0 molar. And I got to find equilibrium concentrations. Okay. Exact same problem as we did before, except now the equilibrium constant is a lot smaller. So I'm just going to set this up. Right. First, I got to recognize this problem. Oh, I'm given initial concentrations. I'm finding equilibrium concentrations. Ding, 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 ding. I got to write an ICE table. Right. So I write my ICE table. I got 1.0 molar here, 0 minus X plus 2X, 1.0 minus X, 2X. Right. My equilibrium constant expression is the concentration of B squared over the concentration of A. Right. Concentration of B goes there. Concentration of A goes there. So I got the Kc, which is equal to 3.3 times 10 to the minus 5 is equal to 2x, the quantity squared, over 1.0 minus x. Okay, now this is the x is small approximation. I say, oh, wait a minute. This equilibrium constant here is pretty small. What does a small equilibrium constant tell you about a chemical reaction?
More reactant, more concentration of reactants.
Correct. It's not going to go very far towards products, right? The amount of products is going to be small compared to the amount of reactants. So what does that tell you about X?
It's small.
Yeah, X is small. If X is small compared to 1, I can ignore it, right? Just like I can ignore the penny in my pocket when I'm weighing myself, right? I can ignore it. I can't ignore X in the numerator. Why? Because that's not addition subtraction, right? That's multiplication. Okay. So I cannot ignore it there, but I can ignore it there. So this becomes super easy peasy to solve, right? I just get 4x squared over 1 is equal to 3.3 times 10 to the minus 5, right? So that's just that. So x squared is equal to 3.3 times 10 to the minus 5 divided by 4. And I solve that for x. And I get that x is equal to 0.0029. Right? So I could just plug that back into here, right? And I can get my equilibrium concentrations pretty straightforwardly, right? What you can do when you do this approximation is you can check, well, was X really small compared to the number I subtracted it from? So I can go back and I say, okay, I subtracted X from 1. So 0.0029 divided by 1.0 times 100% is equal to 0.29%. And here's what I'm going to say for the sake of our class. If this number is less than 5%, then go ahead and make the approximation. Okay. X is small is okie dokie. Okay. If you get that. If you get a number bigger than 5%, then you got to go back and solve the quadratic. All right. But this will save you a lot of time. And this actually has a lot of chemical importance, as we'll see moving forward. So even though you might say, look, I'm just going to solve the quadratic every time so I don't have to worry about it, don't do that. All right. Because I want you to understand this approximation. All right. I want you to understand this X is small approximation because it has a lot of, it turns out it has some chemical significance going forward. Okay. Let's see. I see some questions. Ryland.
Do we ever run into cubics?
Yeah. Yeah. I'll show you one in a minute.
Cool.
Megan.
Do you mind explaining why you dismiss the x in the numerator, but you can in the denominator?
Correct. So let's say I have 99.0 minus 0.0001, right? Compared to 99.0 times 0.0001. When I subtract this number from that number, right, I get 99.0. To the number of significant figures that this is given, this number is so small that it doesn't change the value. When I multiply these two numbers, though, of course, right, what is that going to be equal to? 1, 2, 3, 4. That's going to be equal to 0.0099, right? So in other words, when I multiply a small number by a big number, I cannot ignore the small number, right? When I subtract a small number or add a small number to a big number, if it's really small, I can ignore it. So in the numerator, I was subtracting the x. In the denominator, I was subtracting x from 1. In the numerator, I'm multiplying it, right? So I can ignore it here, but I can't ignore it there. Awesome. Emily.
So I'm just a little, I want to clarify. So you're saying if x is less than 5%, then we can use that shortcut.
Correct.
So to determine that, we still have to solve for x though. Or do we just solve for x assuming that it's small? And then
Exactly right. If you see, you're going to get a feel when you start working problems for when the x is small approximation is valid. And I'll tell you how to look for that here in a minute. But if you're in doubt, if you're kind of at a borderline, just say, oh, let's just assume and see what happens, right? Solve for x. If this had come out to be x is equal to, let's say, 0.5, right? Then I'd go 0.5 divided by 1 is 50%. Oh, I can't do it. So then you go back and you solve your quadratic.
oh, I see. Okay.
Right? So you can just try it. If it doesn't work, then you got to solve the quadratic. What you want to do is you want to just take whatever you find out to be x and divide it by the number you subtract from, and then multiply it by 100%. All right? Okay. Very good. Now, let's do an example. So here we got this reaction, I2 in equilibrium with 2I. Kc is equal to 3.76 times 10 to the minus 5. Oh, small kc. That's the first thing your antenna should go up. Oh, okay. I might be able to make the x a small approximation here, right? Because I have a small kc. And then it's telling you if you have 1.00 moles of I2 in a 2.00 liter flask, I want to find equilibrium concentrations. Oh, ding, 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 right? I have to do an ice table, right? As soon as I'm asked to find, as soon as I know I'm given initial concentrations and asked to find equilibrium concentrations, I write my ice table. Now remember, ice tables always in molarity, right? Never in moles. So I can't just put this 10 moles because that's in 2 liters, right? So what's my concentration of I2? 0.500 molar, right? 1 mole divided by 2 liters. Concentration of I2 is 1.00 moles divided by 2.0 liters is equal to 0.50 moles per liter, right? Or 0.50 molar, okay? So I plug that in. This is 0, right? Which way is this reaction going? To the right or to the left?
To the right.
To the right, right? Minus x. This is going to be what? Plus
2x.
2x, right? So I get 0.500 minus x, and I get 2x. So now I plug into my expression for K. Kc is equal to the concentration of I squared divided by the concentration of I2. I plug this in. Concentration of I is 2x, so I get 2x, the quantity squared, divided by I02, 0.500 minus x. And there's my quadratic, right? Because I know what Kc is equal to 3.76 times 10 to the minus 5, right? So here's my quadratic equation. I can either multiply all that out, right? And plug it in the quadratic formula. But I'm going to say, this is a pretty small Kc, so maybe x is small. So let me try making the X a small approximation, right? Because then that that simplifies the math tremendously, right? Because then I get 4x squared is equal to 3.76 times 10 to the minus 5 times 0.500, right? So x squared is equal to 3.76 times 10 to the minus 5 times 0.500 divided by 4, right? I take the square root of that, and I take the square root of that, and that gives me x. X comes out to be equal to 0.00216, right? So that means that now I want to see, okay, is my X's small approximation valid? Well, I can always just check it. 0.0216. What did I subtract it from? 0.5, right, times 100%. And that turns out to be equal to 0.00216 divided by 0.5, right? That's equal to times 100, 0.432%, right? So is my approximation valid? Yes. As long as it's under 5%, it's valid. Here's my value of X. Now I can just plug into here to get my concentrations. So my concentration of I2 is equal to 0.500 minus 0.00216. That's equal to 0.498. And the concentration of I is equal to 2x is equal to 0.0432. Right, so there are my equilibrium concentrations. Oops. Does that make sense? Emily, you have a question?
Yeah, really quick. So do we just assume that the initial concentration of the product is 0 because we're not given it?
Correct. Yeah, if you're not given a concentration of a product, assume it's 0.
Okay, thank you.
And yeah, I noticed I made a mistake here. It should be 0.00432, right? 0.00432. Thanks, Minerva. Any other questions? Is this making sense?
I got a question.
Yeah.
Why exactly are we dividing the x, the 0.00216 by 0.5?
Great. This is checking X is small approximation, right? So this is how I'm just checking to see if the approximation was okay to do, right? And what I'm saying is that, and the reason I'm divided by 0.5 is because I'm checking to see if this is small compared to that.
Okay.
What I'm saying is that if this number is less than 5% of that number, that's good enough for us, right?
Okay.
And you can go ahead and make the approximation.
All right, that makes sense. Cool.
Great
Thank you.
question. Other questions? Elliot. Oh, that was you. Sorry, Elliot. Okay, any other questions? All right. Now, let me just when you thought you had this figured out, let me throw one more little curveball at you here that will really help you to hopefully understand this even better. And again, I'm going to do a couple of examples. I'm going to walk through a couple of examples from the book. These two problems are identical in every way except one. Okay? So let's read through the problem. You have this reaction. You're given Kc. You notice right away that Kc is small, right? So the minute you see that Kc is small, you should think, oh, I might be able to make the X a small approximation here. All right? You're given a half-liter vessel with a certain number of moles of H2S. So you go, oh, okay, this is an equilibrium problem. Ding, 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 right? The bells go off and you set up your ice table. Fair enough? So here, we got to remember working concentration. So your initial concentration of H2S is 0.25, and these are both 0. Okay? Now, consider this problem right next to it. Notice everything's exactly the same, except for instead of 0.0125 moles, I have 1.25 times 10 to the minus 4 moles. All right. Here I calculate my H2S concentration. Instead of being 0.025, it's 2.5 times 10 to the minus 4. So I set up my ice table, and now these are both identical except this number is smaller. You might be able to see where I'm going with this here. The X is small approximation works when X is small relative to what you're subtracting it from. Okay? So for example, if you're weighing yourself and you have a penny in your pocket, you can ignore the weight of the penny, right? But if you were weighing a mouse, right? And the mouse had a penny in its pocket, you probably couldn't ignore the weight of the penny, right? Because the mouse weighs a lot less than you do, right? And so all of a sudden the weight of the penny becomes significant, all right? So when you're subtracting X from a large number, you can ignore X. But when you're subtracting X from a small number, you may not be able to ignore it. Okay, and that's what this example is trying to show you, all right? So notice this is the thing that's going to be minus X. You're going to see that in a minute. And in this case, it's bigger. In this case, it's smaller. So this is kind of like weighing you compared to a penny. This is like weighing a mouse compared to a penny, right? In this case, you can ignore the penny. In this case, you're not going to be able to, as we'll see, okay? So the reaction goes to the right. I'm going to set it up just like every other one we've done. Minus 2X here because of the 2, plus 2X, plus X. Notice in this case, everything is identical except for that initial concentration, yeah? Go again, next step, I sum these columns, right? 0.025 minus 2X, 2X and X. The only difference is that initial concentration. So see, here I'm subtracting that 2X from a pretty big number. Here I'm subtracting that 2X from a much smaller number. All right? So I got to be careful. I got to use my chemical intuition to know when I can use that X is small approximation and when I can't. All right. So here I plug in, I write the expression for Kc, right? I take those lines from the ice table and I plug them into those concentrations. And lo and behold, I get a cubic equation. Even more fun, right? Even more fun to solve. I say, wait a minute, I don't want to solve a cubic equation. I'm going to make the X is small approximation. So I make the approximation, right? X is small. All of a sudden, my cubic equation is super easy to solve. I just take the cube root of that number, and I get 2.97 times 10 to the minus 4. I decide to go back and check my approximation. I take that number and divide it by the number I subtracted from. It's 1.19%. And I go, yay! I don't have to solve a cubic equation, right? So that works. Now let's go to this side. Everything is identical, but except for I'm not subtracting from such a small number here, from such a big number here, right? I'm subtracting from a much smaller number. Nonetheless, I'm optimistic. I say, hey, maybe I can still make the X is small approximation. So I go ahead and I make it. I solve for X and I find that X is 1.38 times 10 to the minus 5. Then I check it and it's 5.52%. I go, oh, well, maybe it's close enough. Well, if we're using 5% as the guide, then this would not be close enough, right? Under 5% would be okay. Over 5% would not be okay. So you got to draw the line somewhere, all right? In this case, we're basically done with the problem, right? Because we just take what we found for X, plug it in, and we get our equilibrium concentrations, right? In this case, we're not done with the problem. We got to go back to this step and solve that equation. Well, you can also use Wolfram alpha to solve equations like this, okay, which is kind of nice. Before those days, you can actually work it out mathematically, which is a pain and takes a while. But another way you could solve these kinds of equations, it's called the method of successive approximations. All right. And what's that? In that case, you say, okay, I make the X is small approximation. I get my X. I find that it doesn't work, but I can take that X and now use that as an approximation by plugging that X into here. That's called the method of successive approximation. So I'm going to take my X, I'm going to plug it into there. And now I don't have to solve a cubic equation. I get X equals 1.27 times 10 to the minus 5. If you keep doing that, eventually you'll get to an X that doesn't change anymore when you do it again and again and again. All right. And then that means you've arrived at the value of X. Okay. So when you get to an equation like this, there's several ways to solve it. One is this method of successive approximations. Another one is to solve the cubic equation. All right. This is the method of successive approximations. You get the number, you plug in, and you get your concentrations. All right. All right. Any questions on that? You will get a lot of practice working these kinds of problems in the next 3 weeks, right? So there will be a lot of these kinds of problems to solve. For a lot of them, you will be able to make the X a small approximation. For some of them, you will not be able to make that approximation. You need to figure out and be able to know when to make it and when to not. If in doubt, just make it, right? If in doubt, just make the approximation and see what you get. If you get a number that's greater than 5% of what you subtracted from, then you go back to the drawing board and you got to solve the equation.
So, Professor, would it be easier then to just plug in the X values that is above 5% instead of actually drawing it out in the
If
quadratic
it's like,
formula?
especially if it's close like this, then the method of successive approximation works really well because you probably only have to do it once or twice. If it works out to be like 30 or 40%, then you got to go back and solve the equation.
Okay, so if we're in like the realm, then we should just use that.
Yeah. Yep.
Plugging in the X value. Okay.
Yep. Most of the time, it's not going to be a cubic equation. Most of the time, it's going to be a quadratic equation. All right. I won't really give you a lot of cubics to solve where you can't make the X a small approximation. Okay. All right.
Is cubic as high as we're going to go?
Yeah, I think so. I don't think there's anything bigger than that. Yeah, I don't think in the homework there is, but if there is, you'll be able to make the X a small approximation. Okay. So that kind of problem, again, keep that kind of problem in your mind. We spent most of the class time on that type of problem. You're going to see that type of problem a lot, right? So remember, when you see initial concentrations, find equilibrium concentrations, ding, 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 make an ICE table, set it up with respect to X, solve the equation for X. That's the procedure, okay? We have one more topic to cover here in this chapter, and it's called Le Chatelier's principle. And we've seen this a little bit already, all right? But let me just give you what the principle is. If a system at equilibrium is disturbed, the position of the equilibrium will shift to minimize the disturbance, all right? And so we want to look at this with respect to 3 different kinds of changes, all right? A concentration change, a volume change, and a temperature change. All right, so we have, the idea here is that it's simple. You have a system at equilibrium, you change the concentration of something, the system responds to minimize the change you made. Yeah? Similarly, you make a change in volume, the system responds to minimize the change you made. You change the temperature, the system responds to minimize the change you made. All right? Systems at equilibrium respond, they kind of fight back. Yeah? You make a change, I don't like that change, I want to go back to where I was. Okay? That's the idea. All right? So let's look at these 3 things: concentration change, volume change, temperature change. So here we have a reaction. N2O4 goes to 2NO2. All right? Let's suppose it's at equilibrium. So you have a certain amount of N2O4, that's these molecules, and you have a certain amount of NO2, right? That's your equilibrium. Now you're going to disturb the equilibrium. What are you going to do? You're going to add more NO2. So that's going to increase the concentration of these products. What's the system going to do? It's going to shift to the left to try to minimize that disturbance, right? So in other words, if I have a real simple system, A in equilibrium with B, and it's at equilibrium, right? If I add more B, it's going to increase the concentration of B. It's going to shift left. What do I mean by that? It's going to go towards the left side. Some of the B is going to react to form A, right? If I decrease the concentration of B, what's going to happen?
Shift right.
Shift right. It's going to try to make more B, right? Again, when you disturb a system in equilibrium, it's going to fight back to minimize the disturbance, right? So here you can see what happens. Here's the equilibrium. I have NO2 and N2O4. I go along, boom, I disturb the equilibrium because I add NO2. The concentration of NO2 goes up. What's going to happen? It's going to react, go left. It's going to bring that back down. And then, of course, as it brings that back down, N2O4 will go up until it reaches equilibrium again, right? At slightly different concentrations, okay? On the other hand, if I increase the concentration of N2O4, if I increase the concentration of this reactant, boom, that's going to go up, right? If I increase the concentration of that, which way is it going to shift?
Right?
Right, yeah, if I increase the concentration of reactant, it's going to go to product, right? If I increase the concentration of A, it's going to go to the right, yeah? So that's going to be brought back down. The amount of product will go up until it reaches equilibrium again, okay? All right, what about the effect of a volume change? So suppose I have this reaction, N2 plus 3H2 goes to 2NH3, all right? So I have this it's in equilibrium, it's in a piston like this. Now I increase the pressure. I'm sorry, I decrease the volume, which increases the pressure, right? Remember PV equals nRT, right? If I decrease the volume, I increase the pressure, all right? How can the system respond to try to bring the pressure back down according to Le Chatelier's principle? Well, if I take 4 moles of gas and I convert it to 2 moles of gas, that brings the pressure back down, right? So in other words, if I increase the pressure, if I decrease the volume, that increases the pressure, the system will try to bring the pressure back down. How can it do that? By shifting in the direction with fewer moles of gas, right? Since I have 4 moles of gas on the left and 2 moles of gas on the right, it's going to shift to the right. Similarly, if I decrease the pressure, what's the system going to try to do? Bring the pressure back up. How can it bring the pressure back up? In this case, for this reaction, it'll shift left, right? It'll shift towards the side that has more moles of gas, right? Because if I increase the number of moles of gas, I increase the pressure, right? PV equals nRT. Okay, the effect of temperature changes. For temperature changes, it depends on whether the reaction is exothermic or endothermic. So if I have an exothermic reaction, I can think of heat as a product, okay? If I have an exothermic reaction and I increase the temperature, which way do you think it'll shift?
Towards the reactants.
Towards the reactants, right? Because it's going to try to cool it back down, right? If I have an exothermic reaction and I lower the temperature, which way is it going to shift?
Towards the right, towards
Towards the
product.
right. And exactly the opposite is true for an endothermic reaction. For an endothermic reaction, I can think of heat as a reactant, right? So that's endothermic. If I increase the temperature, it's going to shift. Which way?
The products.
To the right, to the products. If I lower the temperature, it's going to shift
Towards the reactants.
to the left, right? Towards the reactants. Okay, these two things do not change the position of equilibrium. If I just add an inert gas, even though it increases the pressure, it doesn't change the position of equilibrium. If I add a catalyst, that also does not change the position of equilibrium. Catalyst increases the rate of a reaction, so it might increase how fast you get to equilibrium, but it won't change the position of equilibrium, okay? So a catalyst has no effect. Inert gas has no effect. All right, let's practice. Here's a reaction. 2SO2 plus O2 in equilibrium with 2SO3. I have delta H is equal to minus 198. So is that exothermic or endothermic?
Exothermic.
Exothermic. That means I can think of heat as a product, right? So let's think of each of these things and figure out which way it's going to shift the reaction. What if I add more O2? Which way is it going to shift it?
Right?
To the product, towards the products, to the right. Okay. I add more of this, it's going to shift it right. Condensing and removing SO3, which way is it going to shift it?
To the right.
To the right again, right? If I remove this, it's going to try to make more of that, right? Compressing the gases. Okay, so I compress it, I increase the pressure. It's going to respond to try to lower the pressure. I need to add G's here.
It's gonna move left.
Press it, I increase the pressure. It's going to try to lower the pressure. Which way is it going to shift?
To the right.
To the right. Why? Because I have 3 moles of gas here. 2 plus 1. I only have 2 moles of gas on this side, right? So if I take 3 moles of gas and turn it into 2 moles of gas, that brings the pressure back down. Are you with me? Cooling the container. So if I if I lower the temperature, which way is it going to shift it?
To the right again.
To the right again, right? Because if I take away heat, it's going to try to make more heat, right? So it's going to shift right. Okay, doubling the volume of the container, expanding the container, right? Expanding the container lowers the pressure. It's going to try to shift to increase the pressure. Which way is it going to shift?
Left.
Left.
Left. Correct. Warming the mixture. Warming the mixture is like adding heat. If I add heat, which way is it going to shift?
To the left.
To the left. Correct. Adding inert gas helium to the container. What does that do?
Nothing.
Nothing. Okay. Adding inert gas does nothing. Adding a catalyst to the mixture.
Nothing.
Nothing. Very good. Okay. Here's a question for you.
Wait, Professor,
Yeah.
if you add inert gas to a closed system, wouldn't that increase the pressure?
Yes, but it doesn't change. The inert gas doesn't change the concentrations of the reactants or products. And so there's no shift in the equilibrium.
Okay.
So in other words, shifting around the reactants and products cannot, well, you can, I show this in the book if you want to look at it, but basically when you compress a mixture of gases, what happens is you increase the pressure and you change the partial pressure of each of the gases, but which changes Q, right? Which then makes it shift. If you add inert gas, you don't change the partial pressures, you don't change Q, and therefore it doesn't shift.
Okay. All right, thank you.
If you're curious about that in more detail, have a look in the book or I can talk to you more about it afterwards.
All right.
Okay, 10 more seconds. See if you can answer this in the next 10 seconds. Okay, great participation. Thanks everyone for answering. The correct answer was B, and a lot of you got it, but some of you missed, a few of you missed that. So let's just look at what happened there. You have this reaction, right? And let's go through each of these. If I increase the volume, what do I do to the pressure?
Decrease it.
Decrease the pressure, okay? If I decrease the pressure, the reaction is going to react to try to increase the pressure. How can it increase the pressure? By making more moles of gas, right? PV equals nRT, right? P is proportional to N, the number of moles, right? So it'll shift left, make more moles of gas, and try to bring the pressure back up, all right? So let's say B, decrease the volume. When I decrease the volume of this thing, right, it's going to increase the pressure. The system is going to respond to try to decrease the pressure. How can it do that? Shift to the right. Take 4 moles of gas and turn them into 2, right? That lowers the pressure back down. So the right answer is B. But let's just look at these other two just because they're here. Increase the temperature. This thing is exothermic, right? Exothermic, so you can think of heat as a product. Remember, exothermic is negative, endothermic is positive. Heat is a product here. If I increase heat, which way does that shift it? To the left, towards the reactants. All right, remove nitrogen. I remove the nitrogen. Which way is it going to shift it? It's going to try to bring the nitrogen back up, so it's going to shift it to the left, right? So it's only B here that shifts it to the right. All right. See, I see a couple questions. Taylor.
When will we know it's an inert gas is added? Like, will it...
Great question. An inert gas is any gas that that's not in the reaction.
Okay.
Right? So in other words, if I add nitrogen, that's not an inert gas. If I add helium, that is, because helium is not in the reaction.
Okay. So like if this example was like, okay, in a container and you're like, we just added argon, but it's not a part of this reaction, then that would be the inert gas.
Correct.
Okay. Okay.
Correct.
Thank you.
Great question. Ryland.
I'm trying to piece together the temperature one. Would I be right in saying that an increase in temperature will shift away from whichever side of the reaction the heat's on?
Correct.
Okay.
Yep, that's exactly right. Okay, very good. Any other questions? Okay, nice work, everyone. Thanks for staying with me. Thanks for your attention and your participation. I really appreciate it. Thanks for having your cameras on. I love to see you. And I'll look forward to seeing you again on Wednesday. Before I stop this recording, I am going to show you how to use Wolfram Alpha. So if you want to learn how to do that, just stick around for a few more minutes and I'll show you how to do that. And then after that, I will continue to take more questions as they come up. And smarter every day. I'm glad to hear that. Thanks, you guys. Have a great afternoon. See you on Wednesday.
Thank you.
Thank you.
Okay, so let me go back to let's say this reaction, or sorry, this quadratic equation. All right. So this is one of the quadratic equations we solve with the X's small approximation. All right. Let me show you how to solve that equation using Wolfram Alpha. So I'm going to bring up my browser here. I'm going to search for Wolfram Alpha. All right. I'm going to go to this website, Wolfram Alpha. And it says, enter what you want to know or calculate about, right? So it's super easy. What I'm going to enter here is I'm going to enter this equation. Oops, sorry. Let me move this over so you can see it. I'm going to enter that equation. Okay, so the way you enter that equation into here, notice I don't even have to put it in quadratic form, which is so nice, right? I don't even have to put it in quadratic. I could just enter it just like that. So it's 3.3. I think you just do exponential minus 5 equals, I'm just going to type 4x squared because that's a little bit easier. 4x raised, let's see, I think the raise is the caret squared, right? And then I'm going to divide that divided by the quantity 1.0 minus x, close parentheses. Okay, so there I've entered that equation. I'm going to hit the equal sign. It'll tell me what it thinks that I entered right here. So in other words, if you type this in wrong, you'd be able to tell right here. So it says that I entered 3.3 times 10 to the minus 5, right? That is equal to 4x squared. So 4 times x squared over 1.0 minus x, right? So this confirms that I entered the equation incorrectly. Okay? You always need to compare this to what you think you entered to make sure you entered it incorrectly. And then you get down here and it gives you the solutions. So in this case, it's saying x is equal to minus 0.002876, or x is equal to positive 0.00286686. 286816. So of course we reject the negative one, and notice that the answer it gave us 0.00286, that's solving the equation exactly, right? And here was our x a small approximation. It gave us essentially the same answer, right? So you get the same answer if you make the x a small approximation, or if you solve the equation, the quadratic equation exactly, right? So this answer here, these answers here would be the same ones you would get if you plugged into the quadratic formula. But Wolfram Alpha does that for you, and it saves you a lot of time and effort. Okay. All right, I'm going to stop the recording right there.